welcome to class. Let's get started with talking about mastering chemistry for a moment. I think some of you guys were frustrated with the homework set that was due last night on some of the Lewis structure questions. And I'm not sure if some of you guys still were stuck on how to enter Lewis structures. And to be fair, I think this is the first time I ever even tried to play around with mastering, and it is kind of stupid. But I thought we could just go through a couple of these real quick and make sure we're all on the same page. Now, the reason why I give all these extra credit assignments is for problems like this. We are going to encounter problems in mastering chemistry that are just tedious and painful, and you may lose points. Even though you know the right answer, you just can't figure out how to enter it. That's why I make extra credit available so you can earn points back, especially in those particular types of moments. And the homework sets are capped at 100%, so it's not like you can go over 100%. So the extra credit just allows everybody to get back to a perfect. So I might start, like this one's looking at HCO2 minus, so I'd probably start with like a carbon atom, and then from there you can sort of start to piece together like your oxygens, maybe with a single bond. You need an oxygen with a double bond, and then we need a hydrogen with a single bond. And now you may have already had the structure written out, but you probably had something like H to the C, double bond to the O, single to the other O, electron pairs, 3 of them are on the single bonded O, 2 electron pairs are on the double bonded O. So we might do 2 electron pairs are on the one O, 3 are on the other. And then the formal charges of everything here are 0 except for this oxygen that ends up being minus. Okay, and so if I entered everything right, tell me it's right. And so then the other tricky part was then the other part of the question. So one of the issues is, does this structure have a resonance structure? And it does, because we could have made the double bond to the O with the other O and the single bond to the other oxygen. So we could have flipped the bonding around. So there is resonance. And then, okay, so what we might do here is copy this whole structure because it wants us to come up with the other resonance structure. And that might be the part where this was kind of tricky to figure out how we do this. So we have to pick like a double bond. To be honest, I don't know why that just switched. I'm doing a couple things. All right, so let me start over again and just move it. Okay. Okay, so I don't know if this is helping at all, as I struggle to figure this out too. But one of the things that I did was I just changed a single bond and then changed the double bond to a single bond. I clicked the double bond that dragged between the two atoms, that switches a single to a double. And then what I need to do to go back to a minus charge is click the minus button, click on the O, and that gets rid of the H. Yeah, so I mean, it's kind of weird on how to go through the particular structures here. But that's sort of the general tasks of this particular problem. So if you were stuck on it, you can still earn a majority of the credit. If the points matter, I know the points matter, but at the same time, you may have earned extra credit points. A lot of you guys already have well over 100%. So if you had missed the points for this question, I'm sure if you have over 100%, it's not going to be anything that causes you to have a lower homework score as a result. So any just general questions on like homework? I know it's frustrating, and I hate when like we're frustrated just on using a piece of technology that we have to use for the class. So hopefully the frustrations are reducing. Okay, so with that, let's head back into the lecture notes. There's a top hat problem that's open as well. We'll come to that in a second. But so what we're looking at here is getting into chapter 9. So chapter 9 is going to get into molecular structure and talk about the shapes of molecules. One of the starting points we'll find is the Lewis structure. So we talked a fair bit in chapter 8 that the Lewis structure itself doesn't necessarily tell us what the real shape of the molecule is. We're going to pick that up here in chapter 9. Another thing we want to talk about is molecular versus bond polarity. we're going to find, and from chapter 8, we're able to look at different types of bonds. Like maybe we can see something like a CF bond is polar from a chapter 8 perspective just because carbon and fluorine have different electronegativities. So this bond here is definitely polar in the sense that the fluorine is going to pull more electrons towards itself and pick up more of a negative charge, carbon more of a positive charge. But something interesting happens with some molecules. If you take a molecule like CF4, so CF4, is that so small? Would have a Lewis structure that looks square planar, but it's really not square planar once we get into chapter 9. What we're going to see is that a molecule that has 4 total domains about a central atom. We have 1, 2, 3, 4 domains about a central atom, that they're going to repel each other and want to get as far away from each other as possible. So a molecule like CF4 ends up becoming tetrahedral in its shape. So one of the fluorines comes out at us, one goes back into the page, and then 2 of the other bonds are right in the plane of our paper. And so this is the real shape of a molecule of CF4. These bond angles turn out to be exactly 109.5 degrees. This isn't geometry class, but if it was, we could go through and sort of prove that a tetrahedron with an atom in the center, that all the bond angles about the atom in the center are going to be exactly 109.5 degrees. So the whole molecule is symmetrical about every one of its bonds. And we call that shape tetrahedral. Now, something peculiar happens for CF4 in that all of those CFs and the fluorine atoms are exactly opposing each other geometrically such that the total dipole moment of the molecule ends up being exactly 0. And the molecule ends up being what we would term nonpolar. So this is a nonpolar molecule despite having polar bonds. So it's not nonpolar because the bond polarities change for some reason. No, the bonds are still polar. All these fluorine atoms pick up a negative charge, but the overall molecule ends up being nonpolar. Now this is going to be somewhat tricky to pick up at first, but the one thought might be if you imagine dangling a charge on one side of the CF4, is it going to flow towards the charge? If we put like a little positive charge on one side of the molecule, you might think, would the molecule sort of like fly towards the charge? The issue here is all those F's are going to almost fight and the molecule is just going to spin, and it's not really going to move towards a charge. We need one side of the molecule to have a different charge than the other side, then the molecule might be able to move towards that particular charge. Okay, so we're going to go through plenty more examples of molecular versus bond polarity, but I just want to introduce right off the bat that we're going to see a concept that seems strange at first. That is, that a molecule like CF4 has polar bonds, yet it's a nonpolar molecule. So the chapter 9 wraps up with some discussion of different types of bonding models. So we'll be getting into those as we progress through chapter 9. Okay, so let's come back to Lewis structures. Chapter 9 is going to be tricky if we can't do Lewis structures. And so let's make sure we have some Lewis structures down pat. So this question here is asking which molecules have only single bonds, no double or triple bonds in their Lewis structures. Okay, so let me see where we're at with the question. Okay, let me give you guys like about 2 minutes to continue working on this problem. Okay, so let's take a look at this one. So let's start with the middle one, ClF3. For ClF3, we might start central chlorine, 3 fluorines attached. That uses 24 of the 28 electrons. There's almost no shortcuts on some of these to know when we add lone pairs onto the central atoms. We just have to count the electrons, start with their structures, starting with the fluorine atoms, and kind of piece it together from there. So at this point, the central chlorine atom has a 0 formal charge, as do the outer fluorine atoms. So there's going to be no possibility for considering double bonds for the middle structure. So that's why ClF3, no double bonds within its Lewis structure, so only single bonds for ClF3. Now for SO3, when we're looking at this structure here where we've done mostly the same thing, we've used all 24 electrons, none left over. And so then the issue here is we should make at least one double bond. Because we make one double bond here, then we reduce down to a 2+ formal charge on sulfur, 0 on the outer O. We're completing the octet of that sulfur now. So this is a pretty good Lewis structure. This is generally one of the 2 accepted Lewis structures that we would generally take. We'd either say this one is the better one because it satisfies the octet rule, or you might keep going with it. You might make another double bond and then another double bond. So another Lewis structure you might write would be double bonded all the way around. And the reason why this one might be acceptable is because you have a 0 formal charge now on all the atoms. So you've minimized the magnitudes of the formal charge with the double bonds. So this one would satisfy the formal charge rule. But you see how either one of those 2 structures uses double bonds. So either one of the accepted structures for SO3 would use a double or triple bond, so not just single bonds. And so then for the diatomic molecules are ones where we're always going to satisfy the octet rule when possible. And so that makes it relatively easy to try to start with the single, see if we have enough electrons, use a single bond. If not, try a double. If not, try a triple. And so then this works with a single bond, because that's 14 electrons. So we use the proper numbers, single bond. So 1 and 2 use only single bonds. Okay, let's do one more Lewis structure problem. Let me also mention, if you didn't get a chance to get candy before class, please get some after class, otherwise you're going to have to eat it all this weekend. We had one trick-or-treater last night, so. But it was, well, it's not awe. I mean, like, to be fair, it's our fault. We were out for like an hour and a half of it. And like usually we take our candy to our neighbor's house. They weren't home, so we were only actually home for like a half hour or so trick-or-treat, so it's mostly our fault that we only had one trick-or-treater. But yeah, it's kind of cold. So which one of these Lewis structures just has a lone pair of electrons on the central atom? Okay, good job on this one. So on this one here, we're just picking up the 3 O's on N with 24 electrons, leaves no electrons behind for the central atom. And so then maybe we make a double bond and then lose an electron pair for our best Lewis structure. We can't expand the octet of nitrogen though, so this is the only Lewis structure that's acceptable for nitrate. For the sulfide ion, we end up adding the 2 electron pairs because we had 2 electrons left over to go onto the central atom. And so then whether you stop at this structure where we're satisfying the octet rule but have a positive formal charge on sulfur, or you make the double bond, those would be 2 acceptable structures. One where we satisfy the octet rule, or another where we maybe satisfy the formal charge rule. Move the electron pair in, make a double, reduce the formal charge down to 0. Now, regardless for nitrate and sulfate, which structure you're looking at, they both should be thought of as having equivalent NO bond lengths throughout the whole molecule, or equivalent SO bond lengths throughout the molecule. So like, let's look at this structure here. This structure here, we have resonance take place that are going to spread those electron pairs out at all times across the other 2 oxygen atoms, such that all 3 of those SO bonds would be more of an order of about 4/3. So 4 bonding pairs of electrons spread across the 3 SO bonds. Okay. So with that, let's head into chapter 9 and get a sense of the different shapes of molecules that we encounter. This example here is CCl4, kind of like CF4, where we can picture a Lewis structure where we have chlorine atoms, each with 3 lone pairs of electrons, and then a bonding pair, single bond between the chlorines and the carbon atoms for 4 total domains. The geometrical way for those domains to spread out the furthest from each other is with an octahedron. So that's going to put the bond angles further away. If you think of the molecule adopting a square planar structure, this would be pretty bad because the bonding pair electrons would now be at 90-degree angles relative to each other. So the bonding pair electrons, there's actually electrons here that are negatively charged in the bond. They're going to repel each other. So there's a model called the Vesper model. The valence shell electron pair repulsion model is basically the idea that the bonding pair electrons and the lone pair electrons of a central atom repel the other bonding pairs and the other non-bonding pairs, and then spread out as much as they can geometrically. Now at the same time, the chlorine atoms are attracted to, like the electrons in the atom are being pulled in by the nuclear charge of the carbon atom. So there's still a reason why the molecule's held together, because the electrons of each of the atoms are attracted to the other nuclei. So the issue is just the molecules are going to try to reduce the repulsions of their valence shell electrons through the types of structures that they adopt. And so then CCl4, just like CF4, ends up being a nonpolar molecule because all of its charge is spread out across the molecule in such a way that every side of the molecule has exactly the same negative charge. So again, try to think, if you dangle a positive charge over here, can the molecule be attracted to the positive charge? And the issue is that it can't. So it's not going to fly towards that positive charge. Okay, now let's think of the shapes of a couple other related molecules, like CH4 takes exactly the same shape as CCl4 because CH4 has the same basic structure of having 4 domains, all of them bonding about the central atom. So the shape of CH4 takes that tetrahedral shape. Then if we look at NH3, the issue with NH3 is it loses one of the bonds and replaces it with an electron pair. So if we're looking at the Lewis structure of NH3, we have the lone pair of electrons, and the lone pair matters. If the lone pair didn't matter, then we might expect this would take more of a trigonal planar type shape, maybe have more like 120-degree bond angles. But the issue is that there's electron pairs on top of the atom, if you think of it, and those electron pairs are going to repel the bonding pair electrons. And the shape of the molecule still looks like a basic tetrahedral shape. But one of the slightly tricky parts of chapter 9 is we try to name just the shape of the actual atoms. The way you actually usually determine the shape of molecules is you pass X-rays through a sample of the compound, and then only the nuclei will deflect the X-rays, not the electron pairs. So usually you just try to think, okay, what's the actual bond geometry of the atoms, even though that geometry is highly dependent on that lone pair of electrons. So we might look at the entire shape of ammonia and say that the electron domain geometry is still tetrahedral. So the shape of the molecule is still defined by the tetrahedral basic shape, but then the atoms, we then would say just are a trigonal pyramidal structure, and their nature. We're trying to name the shape of just these atoms. And so what you see is you have like a triangle of the 3 H's, and then it's in a pyramid shape. So that's why we would call this the trigonal pyramidal molecular geometry for molecules that have 1 non-bonding domain and then 3 bonding domains about a central atom. So anytime we pick up having 1 non-bonding domain and then 3 bonding domains, then we're going to take the shape of this trigonal pyramidal structure. And then water has 2 lone pairs. So of course, we have the 2 lone pairs on water. And so then water is also a triatomic molecule. Anytime we have 3 atoms, our basic question is going to be, are those atoms bent in their geometry, or are they linear and perfectly linear? And so water ends up being bent, where the bond angle is definitely not 180 degrees. It's closer to that 109.5 degree bond angle of a tetrahedral type shape. So the shape still depends on the geometry being tetrahedral for water. So water, just like ammonia, fits into this electron domain geometry of tetrahedral, but then the actual shape of the atoms we call the atom shape would just be bent. So we're classifying the molecular geometry names by either looking at CH4, calling it tetrahedral, trigonal pyramidal for ammonia, and bent for water. These are the molecular geometry names. So it's the shape of just the atom. Sometimes you might think of just like the bond geometry, really the geometry of the actual atoms in the compound. Okay, now another question might be, well, which of these molecules are polar and which are non-polar? One of them is really easy, right? CH4 is pretty easy. Because like if CF4 was nonpolar, CCl4 is nonpolar, then wouldn't CH4 fit into the same category? So CH4 is definitely nonpolar. Now there's another reason why you might classify CH4 as being nonpolar, and that's its bonds aren't very polar either. So the dipole moment of CH4 is exactly 0, just like it would be for CF4 or CCl4. But as well, you may just look at anything with CH bonds and say, regardless of the shape, it was destined to be a nonpolar molecule because the bonds don't have a very big difference in electronegativity. Now, N and H and O, they do have a big difference of electronegativity. Now imagine that we put a negative charge or a positive charge somewhere near a molecule of, say, ammonia. The issue with ammonia now is we have partial positive charges on the hydrogens because they're less electronegative than the nitrogen atom. The nitrogen atom is going to pick up a partial negative charge. So that partial negative charge can then be attracted upward towards that positive direction of an electric field. So ammonia should be able to be affected by an electric field. And so you could look at ammonia and classify this molecule as being polar. So to be polar, you need 2 things. You need polar bonds, but then you need a geometry that allows one side of the molecule to sort of pick up a different charge than the opposite side of the molecule. Water has this ability as well. We have these dipoles pointing in towards the oxygen. Oxygen picks up the negative charge. Hydrogens pick up the positive charge because the hydrogens are less electronegative, oxygen's more electronegative. And so if we put a positive charge over here, the water molecule should be able to move towards the positive direction of the electric field due to its polarity. So water as well would be a polar molecule. So we're doing a few things at once here. We're trying to assess the structure, think about what the shape of the molecule is, and then think as a consequence of the shape and the polarity of the bonds, does the molecule end up being polar? So ammonia, water end up being polar, and then CH4 ends up being nonpolar. Now polarity has a big impact on the properties of a molecule. We won't see some of these or discuss these in more detail until chapter 11, but you can imagine that molecules that are polar are going to be more attracted to each other than molecules that are nonpolar. And there's a few caveats, like if things are relatively equal in size, like CH4 and water are pretty similar in their like atomic weights and their overall size, but water boils and melts at a much higher temperature, and it's because it has that strong attractive nature for itself that CH4 doesn't have, because it doesn't have that built-in polarity or that built-in ability to be attracted to positive and negative charges. So water has a big plus and minus, so 2 adjacent water molecules pretty attracted together. 2 adjacent CH4 molecules, not very attracted to each other. So the melting point and boiling point of CH4 are much lower than something like water. That's more like predicting melting point and boiling point trends is more a topic of chapter 11 that we'll discuss later, but I just wanted to mention there's a fairly big consequence for molecules that are polar versus those that aren't polar. Okay, so let's look at CO2. So CO2, linear molecule now. And the reason why, if you think of the Lewis structure, in fact, every time we draw the Lewis structure, usually we're kind of drawing it in this way here. You can imagine that the electrons in the double bonds want to get as far away from each other as possible. When you have two domains, when we look at these bonds and I say there's two bonding domains, let's be careful at how we define or think of a bonding domain. A bonding domain is just an actual connection of electrons between two atoms. So it could be a single bond, could be a double bond, could be a triple bond, but I just look at one of these as one domain, the other is the other domain. So again, I don't look at a double bond and say that the double bond is two domains or anything like that. A double bond here is just one domain, and the other double bond's the second domain. So there's two double bonds. They're going to want to get as far away from each other as possible. Two things getting as far away from each other as possible, 180 degrees away from each other. Now again, getting as far away from each other as possible would actually be flying away, but remember, the atoms don't want to fly away because they're still being pulled in by the other nuclei. So there's still the attraction of the electrons around the oxygen, and in the bonds here, they're being pulled into the other nuclei. That's why the atoms just don't fly away and the bonds don't just spontaneously break. So there's still a nature of these bonds is holding the atoms together. That's why these molecules exist in the first place. So you have two double bonds, 180 degrees. The oxygens end up picking up the exact same negative charge because they're pulling equally on the carbon. And so then you can think CO2, if we dangle a charge on one side, you can imagine one of the O atoms is like, okay, I want to go after a positive charge. But then the other O says, well, I want it too. And then it just would start spiraling. And so the O would just spin. It would not be pulled towards a positive direction, say, of an electric field. So the molecule would just end up spinning if you were to subject it to such a field. That's maybe one way to try to picture why the overall dipole moment of something like CO2 is exactly zero. So there's no net pull of the molecule towards an electric field. If we dangle another CO2 molecule next to CO2, there's no great attraction either. You just have negative on negative interaction. That's just more of a repulsive interaction. So the CO2 molecules that might be adjacent to each other aren't very attracted to each other as a result either. One of the things in chapter 11 we're going to find, usually things that are bigger tend to have higher melting points and boiling points. That's the halogen trend. Remember how we talked about the halogens in chapter 7 and said F2 to Cl2 to Br2 to I2, that they have an increase in their melting point and boiling point, and that kind of went counterintuitive to the alkali and alkaline metal trends where they actually decrease in their melting point. Cesium almost is a liquid at room temperature. Its melting point's only like 28 degrees C. So the halogens kind of flip because usually being bigger makes it easier for those molecules to be attracted together, that makes it harder to separate higher temperature to melt and to boil. CO2 is a lot bigger than water, so ordinarily you would think something bigger than water that is of this molecular nature, usually that's better for melting points and boiling points, but the melting point is much lower than room temperature for CO2. And it's because it doesn't have that built-in polarity like water does. So water is really special in that it's small, polar, and has the small H atoms to carry that charge. Remember how the lattice energy is higher when you have small ions? That's why hydrogen atoms connected to really polar atoms is pretty effective for making a really polar molecule that can have an especially stable attraction for itself. That's called hydrogen bonding. We'll talk about that more in chapter 11. But water, we get this polarity, and so we get this negative charge, this positive charge, but it's really a consequence of the geometry of the molecule being bent. So for water, we look at the geometry, find that it's this bent geometry because it depends on the two electron pairs on oxygen and the two bonding domains. So for water, we would count there being a total of 4 domains. So 4 total domains, because 2 of them are bonding, and then 2 are non-bonding, the 2 electron pairs on water. So the 2 electron pairs on water are the 2 other bonding or the 2 other domains that factor into the geometry and the shape of water being a bent molecule. So notice CO2 doesn't have any electron pairs on carbon. It only has the 2 bonding domains, no non-bonding domains. So we go 180 and then linear in the shape. So the CO2 molecule, we would say this shape is just simply linear. So whenever we have 3 atoms, like CO2 or H2O, the question is the geometry bent or is it linear? For CO2, it's linear. Consequence, molecule's nonpolar. Water, bent. Consequence, the molecule now is polar in its nature. Okay, let's see if we can just count domains for like SO32-. So think about the Lewis structure of SO32-, and then think about counting up the number of bonding and non-bonding domains. And then it turns out it's not going to matter whether you satisfy the octet rule or the formal charge rule. So no matter which Lewis structure you picture, you should get the same answer for the total number of bonding and non-bonding domains. Okay, good job on this one. So 4 total domains. So we got 1, 2, 3, 4 domains, and only 3 of them are bonding. And then even if you had the structure with the double bond, that's still, so even if you were looking at this Lewis structure, that you would still say that this Lewis structure has 4 total domains. So the double bond still is just 1 domain, 2, 3 bonding, and then the 4th for the non-bonding domain. So then the structure of the molecule should adopt the structure that anything that would take the structure that has 4 total domains, 1 of them non-bonding. So that would be the trigonal pyramidal shape. So the molecular geometry here should be trigonal pyramidal. So central sulfur, electron pair, oxygen going down, oxygen back out at us and away. That's how I might think of this structure here. So you get this like trigonal shape with a pyramid sulfur, making that shape more trigonal pyramidal in its nature. Okay, so let's go through the different types of shapes that we encounter for other types of molecules. So if we have 2 total domains, then the shape would be linear, like CO2. If we have 3 total domains with no non-bonding domains, this would be the case for something like BF3. So if BF3, if you remember, central boron, 3 fluorines, we only have 24 electrons to go around. So it's 3 plus 3 times 7. So this is the case where we remained with a deficient octet on boron. So then we didn't even need a double bond or anything for boron, no lone pairs. So the nature here is going to be exactly 120 degrees in terms of our bond angles. And so then if you think of the boron, if you tried to imagine going to more of a trigonal pyramid shape, that the fluorine atoms are going to have bond angles less than 120. That's going to put them closer together, causing more repulsions. So the issue is, how can we reduce the repulsions of the electrons in the bonding pairs of this molecule? The answer is with the trigonal planar molecular geometry, with exactly 120-degree bond angles. So bond angles across the molecule, all perfectly 120 degrees. Now let's actually picture SO3 for a minute. So for SO3, we might have used this Lewis structure. I think we had this one earlier today. But if we use this Lewis structure here to represent the molecule, we have to then think about resonance for a minute. So think about how resonance is going to make all these bonds equivalent. It's going to make all the bonding angles exactly equivalent in this molecule too. So the bond angle should be still exactly 120 degrees, because really all of those bonds are the 4/3 type bonds and exactly the same as each other. Okay, so even the bond angles in something like SO3 perfectly 120 degrees. Tetrahedral shape, something like CH4, CF4, CCl4 takes that tetrahedral shape. So we've seen a few examples of that already. Now let's actually assess polarity for a minute. So like if we're thinking about the polarity of BF3, would you guys think that's a polar or a non-polar molecule? So the bonds are definitely polar. So the BF bond's polar. So because you may be thinking the two issues, to be polar you have to have polar bonds, but they also have to be arranged in such a way that one side of the molecule picks up a different charge. This is a lot like the CO2 example, where the bonds are polar, you have the negative charge, but it's all pointing in the shape of that triangle. So if we put a positive charge over here, the molecule is just going to spin and not flow towards the charge. So it ends up being nonpolar. So BF3 nonpolar, same thing with SO3 for nonpolar molecule. So molecule is nonpolar despite having polar bonds in those cases. Okay, just like CF4 was nonpolar as well. And CO2, despite having polar bonds, is also nonpolar. So now the other types of shapes we encounter for larger molecules that have expanded octets are trigonal bipyramidal. This is the case for molecules like PF5. If you remember the Lewis structure for this case here, having 5 valence electrons for phosphorus, 5 times 7 for the fluorines, that's a total of 40 valence electrons. This was just the case of having a central atom like phosphorus with 2 fluorine atoms. And then the fluorines here are going to adopt the shape that we call a trigonal. So you get this trigonal shape here, and then pyramidal. So you make a pyramid with the 2 other fluorines pointing up and down. So you get this trigonal bipyramid shape. So we call this trigonal bipyramidal. Now, the shape names, you can memorize the names, but if you look at the structure, I think you can see the trigonal shape and then the bipyramid emerge from this shape here. So you're getting this bipyramid shape about this trigonal structure. So the geometry names should make sense. And if they make sense, hopefully that makes them easier to remember. So PF5, no lone pairs on the phosphorus is sort of the key here. So we have 5 total domains, all of them bonding. Then the molecule adopts this trigonal bipyramidal type shape. And the last basic shape we encounter is octahedral. That's the case where we have 6 bonds to perhaps something like fluorine on a sulfur atom. So we have 6 plus 6 times 7. That's 48 electrons. That's the perfect count for 8 electrons per fluorine. So we have this structure here. And then each of the fluorines would have an octet. That's all 48 electrons. No lone pairs left over for sulfur. Now, if you're looking at the structure, what you might notice is that it would almost be a neat name if they called it square bipyramidal, because like that would be the name just like the one above, where you have like a square shape and then a bipyramid type emerge. But if you notice that this bipyramid structure, on the top half has 4 faces, on the bottom half has 4 faces. That's where you're getting the name octahedral. So this structure here at first might seem confusing that you have a name that says 8. It's like 8 sides, so an 8-sided pyramid emerges, but it's because there's 6 atoms in the structure. So notice that there's not 8 fluorines here, but only 6. So So there's 6 fluorines, but you get 8 sides to a pyramid structure emerge from those atoms in this geometry. So octahedral, I like to think of it as a square plane, and then you have an atom coming straight out and straight into the page. So I think that's one easy way to write this particular geometry. And so now if we imagine the other shapes of molecules, because there's other molecules that are going to have non-bonding domains, what we're going to do is try to count up or figure out if a molecule has 5 domains and one of them is non-bonding, it's going to take the general shape of the trigonal bipyramid. If we have, say, a total of 6 domains, one of them is non-bonding, then it's going to take the general shape of an octahedral structure where one of the lone pairs is residing in one of the octahedral spots. So let's go through some of the different types of possibilities that we encounter. Or actually, before we get there, let's think about how the electron pairs actually dictate an impact structure. So we mentioned that a perfect tetrahedral structure has exactly 109.5 degree bond angles the whole way around the molecule. Now, if you look at ammonia, it fits into the basic shape of being tetrahedral, but notice how the bond angles aren't quite 109 degrees. They're actually a little bit less. What you can work out here is that the electron pairs in the lone pair, you can imagine that they're going to be closer to the atom that they reside on, and that they're going to cause a greater repulsion with the bonding pair electrons, forcing the bonding pair electrons to be a little bit closer in their bond angles. So then you can probably imagine if you had 2 electron pairs to do this, it would be even better. So water has 2 electron pairs that can push the water bond angles to be even less than 109.5, like even a little bit less than ammonia. So notice that what we're seeing here is that the lone pairs are repelling the bonding pairs more than the bonding pairs can repel each other. And that's probably not so crazy to think, because these electrons are just simply going to be closer to the atom that holds on to those electrons, and then the bonds are going to stretch out the 2 electrons in the bonding pair. So the bonding pair electrons are a little bit more stretched out, a little further away from the atoms that they're of the central atom. So the lone pairs just cause a greater repulsion with the bonding pairs. And then we see this throughout. If you look at something like SF4 we're going to pick up has that 5th domain, has a non-bonding pair of electrons on sulfur, and then has 4 bonds to fluorine atoms. So that's going to take the bipyramid shape. Notice that this basic shape is that trigonal bipyramid shape, just where one of the electron pairs resides in one of the spots of the trigonal bipyramid structure. And it turns out that it's a tricky question, but the answer, or like in terms of do we put the electron pairs on the axial type position, or do we put them what you might call the equatorial type position? This is only really an issue with the trigonal pyramidal structure, where we kind of have the choice of do we put the electron pair on this type of structure or over here. The tetrahedral doesn't have this problem. A tetrahedral structure, if you imagine CH4, all those H's are exactly equivalent to each other. So if you're replacing one of the H's with a lone pair making ammonia, it doesn't matter which spot you choose for ammonia, that these H's here just take the other 3 spots that are all the same as each other. But now in the case of the trigonal bipyramidal structure, these 2 fluorines, you might call these 2 axial, the axial positions, and these 3 you might call equatorial. But then what nature is going to do, it's going to choose whichever structure reduces all of the net repulsions. So nature is going to simply go through the process that we might try to consider, that is, which of these structures reduces all of the overall interactions of these electrons with the other bonding pairs. And it turns out for SF4 that it's replacing one of the equatorial positions. But then the impact that this has on the structure is that the electron pair is still here, and it's going to push the fluorine atoms a little bit closer together. So instead of that bond angle being, if you think of this bond angle here, this is only going to be 174 degrees, or 176 degrees, I'm sorry. And so if you think of the angle the opposite direction, where the electron pair is residing, it's now a little bit greater. So the electron pair is pushing the fluorines closer together, so that the fluorine to sulfur to fluorine angle is a little less than 180 degrees. And then the internal fluorine angle should have been closer to 120 if we were in the perfect geometry for a trigonal bipyramid shape, and it's a little bit less than 120 degrees. And then we can also notice this issue with a molecule like Cl2O. This is a molecule called phosgene. It's actually a nerve agent. But the 2 electron pairs in the double bond, there's more electrons in the double bond that cause repulsions with the single bonds in the carbon-chlorine bonds. So 2 electrons cause greater repulsions than the 2 electrons in the carbon-chlorine bonds. causing the carbon-chlorine angle to be less than 120. Notice that the structure of that molecule, it has 3 total domains. It should have been perfect 120. So it should have been perfect 120 degrees if all of these bond pairs repelled each other equally. But what you can sort of pick up is that a double bond is going to repel a single bond more than the single bonds repel each other. Probably not so crazy to think of that as occurring because the double bond has 2 more electrons in it to cause greater repulsions. And then also the double bond's typically a little bit shorter as well because double bonds are shorter than single bonds. So the issue here is we can think about the repulsions of the lone pairs causing greater repulsions with bonding pairs, and then we can think about double bonds causing greater repulsions than single bonds. And that's going to dictate or play a role in the actual structures of these molecules. Now from there, like what I do is just go through some of the different permutations and how we can come up with, for different sorts of structures, go from a Lewis structure to a molecular geometry. Some of these are easier than others, but for HCN, we're probably just making sure we can get to the right Lewis structure. So I'm probably going to use my typical rule for carbon atoms, 4 bonds to carbon, 1 to hydrogen. Nitrogen should have 3 bonds in a lone pair. If I use that as my starting point, then I assign all these 10 electrons pretty easily. So I go 1, or I go 2, 4, 6, 8, and then 10 electrons for this molecule. So now for the central carbon, what I'm probably thinking is what's the geometry about that particular atom? So we have 2 total domains. So do you see how that's just perfectly going to be linear in its shape? So whenever we have a triatomic molecule, 3 atoms, the issue is it linear or is it bent? And this molecule is going to be linear. So this bond angle should be close to 180 degrees. Okay, now, do we expect this molecule to be polar or nonpolar? Now, for it to be so whenever we pick up this bond here, do we think the CN bond is polar or nonpolar? It's a polar bond. Remember, the way I tend to think of polarity is this way here. If you have any of these atoms here, NOF, S, Cl, or Br, these are the most electronegative elements. So if you have anything other than these atoms, if you have anything other than the atom paired with itself in this group here, then it has to be a polar bond. So the CN bond is definitely polar. And then the molecule is also polar because we have a different charge on opposite sides of the carbon. So in order to call a compound nonpolar that has polar bonds, I want there to be exactly the other atom on the opposite side, or on every corner of the molecule. So this molecule here, polar molecule, polar bonds. So how about ozone? For ozone, this, let's not have the same issue we had last time, where I almost lost it on a Lewis structure. 3 times 6, 18 electrons. And then our structure here is going to have the lone pair on oxygen. We ended up with the double bond on one of the O's, single bond on the other. But resonance is going to equalize those 2 bonds, so they're going to be exactly 3/2 bonds of the same length. But that doesn't quite come into play here, because all we have to really pick up is I have 1 domain, 2 domains, 3 domains. So I have 3 total domains about this atom, or about this molecule. So it should take the general shape of a trigonal planar type structure, but then with an electron pair in one of the spots. So do you see how that's all I really need to know, that this molecule here has to be bent in terms of its geometry? So not linear. So it's not going to be 180 degrees because of the lone pair of electrons and the basic shape of the molecule taking the trigonal planar electron domain geometry and then the overall geometry of the atoms of just simply bent. Okay, so anytime I have 3 atoms, the molecular geometry name is either linear or bent. And it's linear. I can't have any lone pairs on the atom for it to be linear, though. So for OF2, we have 6 plus 2 times 7. If we remember the oxygen, the 2 fluorines, this is probably a good reminder that we might draw a structure that looks linear. When I sketch a Lewis structure, I'm not really thinking too hard. I'm just trying to figure out what the structure of the molecule is. I take my total of 20 electrons. I've used 16 of them. The 4 leftover electrons go on the oxygen atom. 0 formal charges around, so I know I have a good Lewis structure. Now, the issue here is we just have to resist the temptation to call this linear, because it looks linear. Like I sketched it linear, but it doesn't mean the real molecule is linear. This is just a Lewis structure. The real shape of this molecule has to be bent. Why does it have to be bent? Well, it's because the molecule has to adopt the shape of a tetrahedron. So we're going to have a lone pair and a lone pair, and then the fluorine atoms coming at us in a way. For a set of bond angles here for the FOF bond, that should be definitely less than 109.5 degrees in terms of the bond angle here. We can think of some of these issues, like in the case of ozone. We expect the bond angle is probably close to 120, but probably not exactly 120. So we look at this bond angle here. We probably expect this bond angle to be a little less than 120 degrees due to the greater repulsions that those bonding pairs are going to have with the lone pair on the central O. So we can come up with some predictions of bond angles of where we expect them to be close to. That's the closest angle in the geometry that the molecule is falling into. And then we can think of if there's some lone pair repulsions that might impact those bond angles. Let's see if we can't just press forward for a couple more examples. Because we were talking about SF4 earlier, where the issue with SF4 is we end up with that lone pair, and we ended up in this geometry here. But the question is, how do you name that shape? Or like, how do you put a name to the geometry of the molecule? Well, the geometry name is actually named for this molecule looking almost like a teeter-totter or a seesaw. So the geometry name of this is often called seesaw, because it looks like a seesaw. If you imagine a molecule that looks like this, then it just looks like a teeter-totter or a seesaw. So that's where the molecular geometry name is coming from, is looking at the actual shape of the atoms and then trying to come up with a name that fits the shape. So for something like ClF3, the issue here is we end up with 2 lone pairs on chlorine. So I have chlorine with 2 lone pairs. The structure actually does adopt the shape that's pretty close to this structure here, other than one of the electron pairs is coming out at us and another into the plane of the screen. And so this molecule here does take a shape that's like this, because what this molecule is doing is it's trying to take that general shape of a tetrahedron, or of a trigonal bipyramid, but where we have the electron pairs going into the page and then out of the page. And so the issue with this molecule is, what do we call this shape here? Well, we end up calling it T-shaped. So this molecule here, we call this the T-shaped geometry because it looks like a T. So you're trying to look at the shape of just the atoms in the molecule. Even though the atom shape are defined or dependent on all the electron pairs, the electron domain geometry of ClF3, just like SF4, just like PF5, these are all still fitting into the trigonal bipyramidal electron domain geometry. So the geometry is still dependent on all of the total domains being equal to 5. But then the shape of the molecule, we put a name to that, in this case here, just being T-shaped. We'll pick up with xenon F2. Next time it ends up being linear, but we'll pick up with that one on Monday. All right, guys, have a great weekend. See you back here next week. Get some candy.